Okay. Then in this part, I will present a new feature of CLASP. Specifically, this presentation will be divided in two. In the first part, I will present how we can search for differential linear distinguishers using CLASP. And in the second part, I will present how you can use a division property to analyze ciphers. Okay, let's move then to the first part of the presentation. And in this first part, as I mentioned, we have a feature to search for a differential linear distinguisher in CLASP. And first, we need to very quickly recap what is a differential linear distinguisher. So a differential linear distinguisher, we can see, roughly speaking, that it is a pair where the first element of this pair is an input difference, while the second one is an output mask. A certain cipher has this particular distinguisher if you generate, for example, a random plain text, and after you apply the input difference, and you encrypt the cipher, and after you compute the output difference, and after you apply the mask, and you repeat this process many times, and if this the correlation of these experiments is high, then you can say that you found a distinguisher. Okay, so here we have a representation of a cipher. Okay, to find these differential linear distinguishers, one usual method that is being used right now is to split first the cipher in three parts. As you can see here, we divide the cipher in E1, EM, and E2. And we have here the input difference, and in the end, the output mask. Okay, the first part or the top part, for the top part, you need to find a differential distinguisher. In this case, this differential distinguisher is happening with probability P. And for the middle part, you have a differential linear distinguisher. It usually consists only of a small number of rounds. And here, the correlation we are representing with R. And finally, you have in the bottom part the linear approximation that is happening with correlation Q. Okay, so now let's see how we can find this distinguisher, or how we can use CLASP to find this kind of distinguisher. But before that, I would like to mention that the correlation of this distinguisher, knowing P, R, and Q, is equal to this expression here, P R Q squared. This is the total correlation. If you want to distinguish a cipher from a pseudo-random permutation using this correlation, then you need to use this amount of plain text. It's an epsilon times P to the minus 2, R to the minus 2, Q to the minus 4. Okay, so then now let's move to the how we can use CLASP to find a differential linear distinguisher on a spec reduced to six rounds. So first of all, what we need to do is to instantiate a class spec block cipher that is a class from CLASP that is containing the spec block cipher. Okay, and you need to pass, and we are passing here the number of rounds that in this case is equal to 6. And here I'm only printing this cipher using this method print. And as you can see here, and also as Emma mentioned, we can find here some details of this cipher. As for example, which are the cipher inputs, which are the cipher input bit size, 32 for the case of the plain text, and 64 for the key. We have the cipher output bit size, that is 32, the number of rounds. We have also details of the components, as Emma already explained. For example, we have here that this component is representing a rotation by 7, okay, of the 16 first bits of the plain text. After we have, for example, one modular addition, and this one modular addition is being done on the output of the previous component, and also in the second or in the last 16 bits of the plain text. Okay, so now let's move on to how we can map which rounds will be those in the top part, which will be those in the middle and in the linear part. So in order to do so with CLASP, we can do this very easily by using this method from the class Cipher that is called get components in round. With this one, you need to pass the round number and you will get all the components in a specific round. Okay. So we are defining here that for the rounds 1 and 2, we have that are the top part components. For the rounds 3, the round 3 is only that one in the middle that belongs to the middle components, the middle part, while the rounds 4 and 5 belongs to the bottom part component. Okay. Then here I'm printing only these components for the top, for the middle, and for the bottom part. And after I'm creating a dictionary with these components, specifying which of them are middle part components, which of them are in the linear part. Okay. And as you can see here, I'm not adding the top part components because these top part components can be inferred from these middle part components and bottom part components by doing only a subtraction. Okay, here then we are using the class SAT differential linear model. This class is implementing some techniques to search for differential linear, and for linear distinguisher for each part, of course. And in this class, we are using for the top part and for the middle part, we are using basically Liebman-Moriai techniques. Well, for the linear part, we are using the techniques that are implementing in this other paper here, in this second bullet. For the middle part, also, I would like to mention here that we are using truncated differentials. Specifically, we are using bitwise deterministic truncated differentials. And then what we need to do is to pass the cipher spec, reduced to 6 rounds, and we need to pass also a list, a dictionary containing the structure of the rounds, which are the top part components, the middle, and the bottom part. So after that, we are going to find actually the distinguisher, and in order to do so, first we are using this set fixed variables helper that will help us to add some constraints to the model. Okay. For example, here we are saying that the plain text should have at least one active difference. Okay, and we are saying also that for the key difference, all their values should be equal to 0. Okay. For the cipher output mask, of course, we need to have at least one active output bit mask. And something that I would like to remark here is that this set fixed variables method is not only for these specific components. You can use in whatever components you want to add constraints to your models. After we are using then this find lowest weight XOR differential linear trail that will do this task of find a distinguisher. Okay, but before we need to pass the constraints that I just mentioned. And we need to pass also the solver name. We have in class many solvers. For in this case, we are using SAT techniques. We have Cadical. We have also some parallel versions. For example, ParKeySat. We have KeySat, CryptoMinisat, and etc. And also, we need to pass here for the truncated differential the number of unknown bars. In this case, I'm adding 8, but will be 7. It depends on how far you want to go with the number of unknowns variables here. And after I'm printing the trail, okay, after running this, You can print the trail, and using a preprint to do so. And here we have the trail, and as you can see in this trail, we have information about the trail, of course. For example, you have here the okay. For example, you have here the plain text somewhere here. I need to. Here, for example, you have the input difference, okay? And after the first round, you will have this output difference here, this one here. And after one more round, you will have this output difference here. As you can see, those ending in 11, in the suffix 11, are intermediate values of the case schedule, while those, mainly those ending in the suffix 12, are those from the permutation. Okay, so I was saying that we have here the output difference after the second round. And for the third round, as I mentioned, we are using truncated differentials to model this. Then we have this output difference. But as you can see here, we have some unknowns variables that are being the unknown variables are the unknowns, sorry, are being represented with the symbol, this symbol here, interrogation. Okay, something else that I would like to mention here is that you can see that for the top part, so for the first and the second round, the values are in X strings, while for the third round, that is the truncated one, it is in binary string. The same occurs with the linear part. For the linear part, the output masks are in X strings, okay? And you can see here, after another round, which is the linear mask, which is another linear mask, and finally, is the cipher output somewhere here. Yes, we have the cipher output, output mask here. Okay. So let me move to the next. Okay, here I'm printing only the distinguisher, which is the input difference, which is the output mask. Also, as Emma mentioned, we have this nice class called report, where you need to pass only the dictionary containing the trail, and you can use this method show to have a nice print of the trail. So the dash here means that is not active difference, while the one, of course, is the opposite. And here we have the intermediate values after the round, 1 round, 2 round. For the third round, as you can see here, we have these symbols that are representing the unknowns in the truncated differential. And here we have the output mask. Okay, and something else that I would like to remark also here is that in CLASP, we are representing each component. In each component, we have a suffix. And this suffix, as you can see here, contains 2 numbers. The first one is representing the round number, while the another one, the next one, is representing the position of this component on the round, in the round. The total theoretical weight here is 10, okay? And since we are working in the single key scenario here, the key flow for the differential, truncated differential, will be equal to 0. And after that, we are going to check the distinguisher. Actually, we are going to compute experimentally the correlation of the distinguisher. Sorry for the for this typos here. Okay, so we are using the helper differential linear checker for block cipher single key. This differential linear check, this helper will help us to, as its name saying, to compute the correlation experimentally using NumPy in this case. And here we are passing, of course, as parameters, the input difference, the output max, the key difference, and the number of samples that we want. And finally, we will find the correlation. So the experimental correlation here is 4.7, while the theoretical, as I mentioned before, is 10. So let me move then to the second part of the presentation, to the search of distinguishers, for example, integral distinguishers, or how to mount cube attacks using the trace subdivision property with unknown subset. This is another variant of division property. Okay, and this part of the presentation will be divided in two parts, basically. In the first part, we were analyzing a TOESPN cipher, while in the second part, I will present how to perform cube attacks on this TOESPN. If there is time, I will also go to the how we can search for integral distinguishers on as a very recent cipher that is called Arari. Okay, let's move then to the TOESPN cipher, that one that already Emma present is the same cipher. So basically, in the first round, we are XORing the plain text that is of size 6 with a key, but the key first needs to be rotated by 1. And after, we are passing through the nonlinear layer to these two S boxes. After, we are doing a rotation again, and the second round is basically the same of the first round. Here we have the cipher output, and in the cipher output, from here to the end, the position 0, we mentioned many times position 0 refers to the MCB of the cipher output. Okay, so let's first then define the cipher. We are using this class TOESPN2 that already we implemented in class. And we are printing here this cipher. And I won't go to the details of this print because I already explained in the first part. And after, what we are doing is we are using one of the first methods that will help us to find the ANF of the output bits of the cipher. Okay. In order to do so, we need to use this class, MILP division tree model, and as its own name is saying, this implements the division property techniques, this variant that I mentioned before, using MILP techniques. And in this case, we are connecting to our servers through VPN to use Gurobi. Unfortunately, for now, in the cloud version, we don't have Gurobi because due licensing reasons. Okay. So then, using this class, you need to use this class, and you need to pass the cipher. In this case, we are passing the TOESPN cipher. And here there are some lines that will help us only to hide some prints that are coming from Gurobi. Okay, and after that, what we are doing is we are using this method, find ANF of a specific output bit. Which output bit? The bit at position 0. So here I'm printing the monomials that belongs to this ANF. And here there is a snip code only to parse this list and to show the as a sum of products this list, because as I mentioned, this is ANF. This is an ANF. Okay, this is the ANF then of the output bit 0 after 2 rounds of this TOESPN cipher. And after here we have a way to another method that will help us to I'm sorry, this is the same method, but now we need to pass one more parameter, that is the fixed degree. And with this fixed degree, we are only taking into consideration the monomials with degree 2 from the same output bit, okay, the output bit 0. We can use also another method that is called find degree of a specific output bit, and this will tell you, as its name is saying, which is the degree of the ENF for this cipher output bit. In this case, the 0, 1. The degree, as you can see here, is equal to 4. And one thing is that we can use these methods not only for the cipher output, as I was doing right now, but you can use also for intermediate components. So here I'm printing all the intermediate components of this cipher, and I'm using the find ANF of a specific output bit, but now I'm choosing a specific component, the component SBox03 at the position 0 as well. So here is the list of monomials that belongs to this ANF. And now let's see how we can perform a cube attack on this TOSPN cipher. So first of all, we need to recap very quickly that a Boolean function fx going from f to n to f2 can be represented in this shape here. That is a multiplication of this monomial xu times px plus qx, where xu is basically this, if we expand this xu, is this expression here. As you can see, the coordinates of x are being doing power 2 to the coordinates of the vector u. So this vector u belongs to f2n as well. And then we can construct with this u a set cu, and this cu will be basically a set where their elements are being obtained but iterating over all active bits in U. Okay, and the result then is that if you compute the XOR sum over this set CU, but of course evaluating on the cipher F, then it will be equal to PX only if the monomials that are in key X are not divisible by XU. Okay, this PX is called of superpoly, and more specifically, it's called the superpoly of the cube CU. Okay, let's see then how to find the first term, this XU times PX, using clasp. With this U equal to this vector here. So the vector that is active at the positions 2 and the position 5. In order to do so, we are using the check presence of particular monomial in a specific ANF. That this is a method that is presented in class. In particular, we will see here that we are using this method to check if the monomial P2 times P5 is present or not in the ANF of the output bit 0. Okay. Actually, we are going to retrieve all the monomials that has this monomial P2 times P5. So then the result will be this value here, this ANF here, P2 times P4 times P5 plus, as you can see, each term here has the monomial P2 times P5. Of course, to find the second term, sorry, this term here, QX, you can simply do a subtraction of the ANF at the output bit 0 minus this first term to find the other monomial, the KX. And now let's see how we can compute CU. As I mentioned, this is a set that will contain vectors that are obtained after iterating over all possible values in the vector u. So in this case, we will have four vectors belonging to this CU set. Here I'm simply, in these lines, I'm simply printing this set, and also I am applying the cipher to SPN to each of these elements of this set. We can see that if we sum over CU, it is only a check to see that summing over CU, QX, as I mentioned before, should be equal to 0. This snip code is only checking that. And of course, summing over CU is, as I'm printing here, is equal to 0. And summing also over XU, the XU will be equal to 1. So now we have here the super poly PX, and as you can see, if you sum the first bit of the ciphertext 1, 1, 0, 0, it will be equal to 0. This is why the super poly here is equal to 0. So now if we are working with the non-plain text attack, so if we know this before, then of course we can manage to recover K3. So I will stop here. So I think now I will hand over to David to explain the next part of this presentation. Thank you.